what if we could teach a machine to feel? I'm not just talking about touch, but to actually perceive the world the way we do. Today, we're diving into the incredible science behind neuromorphic sensors, which is a wild new technology inspired by, well, the most amazing sensory organ out there, our own skin. So let's just start with this one big question. What if robots could feel? What if a robot could tell the difference between a perfectly ripe tomato and one that's still hard and green? Or imagine a surgeon's tool that could literally feel the texture of human tissue. This goes way beyond simple touch. We're talking about giving machines a really nuanced, almost human-like sense of the world. And right at the heart of this whole revolution are these skin-inspired sensors. The best way to think about them is as a kind of artificial skin. It's made from these flexible, stretchy materials that are engineered to copy our own ability to sense things like pressure, heat, texture, you name it. So, here's how we're going to break it all down. First, we'll look at our own skin as the ultimate smart sensor. Then, we'll get into this huge data problem that's making today's robots kind of clumsy. After that, we'll explore the solution, thinking like a brain with neuromorphic computing. We'll look at its building blocks, check out some mind-blowing applications, and then we'll wrap up by looking at what's next for the future of touch. If you want to build a better sensor, you first have to study the original masterpiece, and that's our skin. It is an unbelievably sophisticated and adaptive organ that really sets the bar incredibly high. I mean, just think about it. Our skin is this multifunctional marvel. It's not just about feeling pressure or if something's hot or cold. It can pick up on the tiniest change in texture, the strain when you stretch, the humidity in the air. It can even detect biochemical signals. Trying to replicate that entire range of perception, that's the moonshot for artificial sensors. So, you might be wondering, why can't we just slap a million tiny sensors all over a robot and call it a day? Well, it turns out, when you create that much sensory data, you cause a massive, massive traffic jam. Yeah, just try to imagine every single one of those sensors firing off information to a central computer all at the same time. The sheer amount of data is just overwhelming. It creates this huge processing bottleneck, which means things get slow, robots get clumsy, and it burns a ton of energy. And here is the absolute core of the problem. It's a challenge that's been around in computing for more than 70 years. See, in a normal computer, memory and processing are in two different places. So data has to constantly shuttle back and forth, creating that traffic jam we just talked about. It's called the von Neumann bottleneck. But the human brain? Oh, it's a masterpiece of efficiency. Our memory and processing are woven together. Information gets handled right on the spot, locally and super efficiently. And get this for a comparison. The human brain does all of its amazing work using only about 20 watts of power. That's less than a dim light bulb. A standard computer trying to do similar complex stuff, it can chew through over 250 watts. That's just a gigantic difference in efficiency. So to solve that data jam and the crazy power consumption, engineers did what they do best. They looked to nature for inspiration. And the solution is this whole new way of thinking called neuromorphic computing. It's all about building electronics that basically think like a brain. Okay, so what you're seeing here is pretty much the blueprint for this new approach. Just look at how it brings everything together. You've got the skin-like sensors at the bottom, then the neural devices that process all the data, and the algorithms that learn from it. And it's all integrated into one single smart system on a chip. It's a totally holistic design, just like our own nervous system. So let's just quickly break down that workflow. It's actually pretty simple. On the left, the sensors are gathering all the raw data from the world, pressure, temperature, you name it. That info then flows to the neural devices for some initial processing. And then these brain-like algorithms make sense of it all, which leads to an intelligent response in real time. It's just a seamless flow from feeling something to doing something about it. All right, so what are these new systems actually made of? It really comes down to two main things. Brand new kinds of hardware that act like artificial nerves, and new software that, well, speaks the brain's language. So the first piece of the puzzle is something called a memristor. The easiest way to think about it is as an artificial synapse, the little connection point between neurons in our brain. And its killer feature is that it can remember its own electrical state. That means it can both process information and store it, all in the very same place. Game changer. And hey, this isn't just some theory. What you're looking at right here is a microscopic image of a real-life memristor. This one is made from chitosan, which is a material you can find in the shells of crabs and shrimp. How cool is that? This tiny little device can both perceive signals and process information, just like a biological synapse. Now, working alongside those memristors, we've got synaptic transistors. These little guys mimic another really crucial feature of our brains called synaptic plasticity. All that really means is that the connections between these artificial neurons can get stronger or weaker over time, based on experience. And that ability to adapt and change, well, that's the foundation of learning. And then you've got the software side of things, with what's called a spiking neural network, or SNN. So if you look on the left, traditional neural networks are always on, constantly processing a stream of data. That takes a lot of energy. But SNNs, over on the right, are different. They're event-driven. They only fire up and use power when they get a spike of information, just like our own neurons do. This kind of on-demand processing makes them unbelievably energy efficient. Okay, so now that we have all the building blocks, let's look at the really fun part. What can we build with them? From smarter robots to revolutionary healthcare, the future of this tech is all about feeling. First up, we've got soft electronic skin, or e-skin for short. As you can see in this picture, it's this flexible, stretchable material that's just packed with sensors. When you apply it to something like a prosthetic limb or a robot, it mimics the sensory feedback of our own skin. This allows for way more natural, intuitive interactions with the world. And that leads directly to much, much more intelligent robots. I mean, check out this robotic hand. It uses an artificial tactile neuron to actually learn how to grasp an object with just the right amount of force. It's not just following a program, it's feeling its way through the task, adapting in real time so it doesn't crush the object. That's a huge leap forward. But the potential in healthcare is just, wow, it's truly transformative. Imagine a smart bandage, or maybe a wearable patch like the one you see here, that can precisely measure force, strain, and how your body is moving. This kind of 3D e-skin could give us a constant stream of real-time data for everything from medical diagnostics to physical therapy and even proactive health monitoring. So this technology is obviously incredibly promising, but let's be real, we're not quite living in a world full of feeling robots, at least not yet. Researchers are now really focused on clearing the final hurdles to make these systems a part of our everyday lives. The big challenges right now are all about scale and integration. Scientists have to figure out how to build these massive sensor arrays without all the signals interfering with each other. They need to keep making the components smaller and smaller. And, most critically, they've got to perfect that system-on-chip tech to pack all the sensing and brain-like processing power into a single, tiny, super-efficient package. Which really brings us to our final thought for the day. This isn't just a story about better sensors or faster computers. It's about a fundamental change in how machines will perceive and interact with our world. So the big question I want to leave you with is this. As machines actually learn to feel, how is our relationship with them and with our world really going to change?